Hello guys, in this video we are going to be discussing the solution to the problem count triplets that can form two arrays of equal XOR. This is the problem of the day in Leetcode today. So basically in this problem what we have to find is we have to find three indices such that the total XOR the three indices should be I, J and K such that the total XOR from index I till index J not including index J should be equal to the total XOR from the index J to the index K. So, so the total XOR from the index I to the index j, not including j, is given as here, and the total XOR from the index j to the index k is given here. So these two values should be equal. So we have to find how many number of pairs are there, how many number of triplets, not pairs, how many number of triplets are there that satisfy this particular property. Uh, so these are the test cases that they have given us. I will explain with the help of these test cases. So this is the array that they have given us, and these are the valid triplets for this particular array. Now the first triplet is 0, 1, 2. So the total XOR from 0 till 1, not including 1, is equal to the total XOR from 1 to 2. So so we will find the each of the XOR individually. The total XOR from 0 to 1, not including 1, is the total XOR of the 0th index, right? So that's equal to 2. Now the total XOR from 1 to 2, total XOR from 1 to 2 is the XOR of index 1 and index 2. That is the XOR of 3 and 1. That is also equal to 2. So the total XOR from I till j, not including j, is equal to the total XOR of j till k, which are both equal to 2. So this is a valid triplet. Now we will consider this triplet. Inside this triplet, I is equal to 0, j is equal to 2. So for the first part, we have to consider the indices 0 till 2, not including 2. So 0 till 1. So what is the XOR of 2 and 3? The XOR of 2 and 3 is 1. Now for the second part, we have to consider the XOR of the values from 2 till 2. So that basically means the XOR of the index 2. The XOR of index 2 is the XOR of value 1. The XOR of value 1 is 1 itself. So the XOR of the first part is equal to the XOR of the second part. So this is also a valid triplet. So that's how we have identified these triplets. Now I will show you two codes. The first code is a brute force approach, in cube approach. It's not basically a brute force. We are using one optimization called prefix array. But basically it's a brute force, and I will show you another more optimized approach after that. After that I will show you a O n square approach. I'll first show you a O n cube approach, O n cube approach. After that I will show you a O n square approach. This is the O n cube approach. So why is it O n cube? Because I'm using three for loops over here. Three for loops. The three for loops are used to compute the value I, the value j, and the value k. Those are the indices on which we want to split the array. And we are also finding the prefix array. What do you mean by prefix array? Inside this prefix array, the prefix array of index I means the total XOR of all the values till the particular index I. So inside this the prefix of I will store the XOR of all the values till that particular till that particular index and including that particular index. So how will we find prefix of the index I? The prefix of index I can be found by including the current value to the prefix of I minus 1, I minus 1, right? The prefix of I minus 1 will store the XOR of all values till I minus 1. So if we include the current value to the XOR of all the values till I minus 1, we will get the XOR of all the values till the current value. So that's how we compute the prefix array. Now, how will this be useful for our problem? So, in our problem, what we will do is that, so to compute the first part is the XOR of all values from I till j, not including j. So basically, it's the XOR of all the values from I till j minus 1. I till j minus 1. So when we use the prefix of j minus 1, we will get the XOR of all values till j minus 1. But that will include values before I. So suppose uh, A0, A1, A2, A3, A4, A5. Oh, I just realized that it would be hard for you to see the problem. Okay, suppose the value I is 2 and the value j is 4. So suppose the value j is 5, so the value I is 2 and the value j is 5. So to compute the XOR of all the values from uh, I is equal to 2 till I is equal to j is equal to 5, not including j, we have to find all the values, the XOR of all the values from I is equal to 2 till j is equal to j minus 1, which is equal to 4. So we have to find the XOR of all the values from 2 to 4. But to find 2 to 4, we can either use a for loop, but that would be time complex. That would be more uh, computationally expensive again. Or we can use this particular prefix array. Using this particular prefix array, what we can do is that we can find the prefix array till 4, and we can find the prefix array till uh, uh, 1. Why are we doing that? Okay, I'll show you. What do we mean by the prefix array till 4? The prefix array till 4 will include A0, A0 XOR A1 XOR A2 XOR A3 XOR A4, and the prefix array till 1, even though we have to find the values starting from I, we are computing the prefix, the second prefix still only 1. Even though we have to compute the values from I is equal to 2, we are only computing the prefix from prefix till 1. We are doing this because whatever we are taking in this prefix, it will get cancelled. So we don't need I is equal to 2 to get cancelled. So that's why we are taking only the prefix till uh, the previous value of I is equal to 2. So we are taking this second prefix to delete this particular prefix from the first prefix. The first prefix contains all the values from 0 to 4, but actually we only need the values from 2 to 4. So we need to delete the values A0 and A1. So to delete A0 and A1, we are taking the prefix of 1, which will be equal to A0 and A1. Okay, now if we do prefix of 4 XOR prefix of 1, what will happen is that we will get something like this. we get something like this. Now, according to the XOR property, if two similar objects, similar elements, similar values are taken XOR, it will get cancelled and become zero. Similarly, if two similar values over here are getting XOR as well, so it will get cancelled and will become zero. So the resulting value that we will obtain will be equal to the values from 2 till 4. So we are using the second prefix array to cancel the values before 2. So that's what we are basically using the prefix arrays for. So we will get the prefix array from 2 till 4. So in the first part we want the prefix array from I till j minus 1. So we need the prefix array from I till j minus 1. So I'm taking prefix of j minus 1 XOR prefix of I minus 1. Since I need the prefix of I, I'm not uh, I'm not XORing prefix of I. I'm XORing prefix of I minus 1 because we want to cancel the all the elements before I. Okay. And why are we using this extra condition over here? This extra condition is to handle the condition of underflow. So sometimes I minus one will go to the negative. So if it goes negative, negative one, I am like there is no prefix of negative minus one, right? So I am instead giving the value zero when it becomes negative one. And to compute the second value, what we are doing is we want to compute the XOR values from j till k. So I am XORing prefix of k XOR prefix of j minus 1 because we want to cancel the prefix of j minus 1 from the prefix of k. So we are doing it, and I am checking whether the first part is equal to the second part. If they are equal, I am incrementing the total count. So that's basically the O in cube approach. I will show you the O in squared approach. O in squared approach is also similar, but it requires an additional observation. Now I will show you the second approach, which is the more optimized approach. In this approach, we are only using two for loops. That is the main advantage of this approach. Here also we are using prefix array, but we are only using two for loops, so the total time complexity will only become n square. So how are we performing this approach? In this approach, what we are basically doing is that uh, we are taking, okay, suppose uh, what is A? A is the XOR of all values from I till j minus 1, right? And what is B? B is the all the values XOR of all the values from j is equal to k. What do we want to make? We want to make A is equal to B. Now suppose we XOR both sides of this equation with B. A XOR B is equal to B XOR B. It will become equal to A XOR B equal to 0, right? Because the according to the property of XOR, if equal terms are XORed, it will become equal to 0. So we understood that for this property to be satisfied, we just need to find and subarray such that the total XOR of the subarray is equal to 0. So we need to just find a subarray from index p to index q such that the total XOR of this the total XOR of this subarray is equal to 0. If we find a subarray like this, we will be able to split the subarray uh, into indexes pq pjq pjq such that the XOR from P to J minus 1, the total XOR from P to J minus 1 will be equal to the XOR of J till Q. Uh, yeah, so I'll give you an example for this particular test case. I'll provide you with an example test case for this one. So the example test case that I'm going to provide you is 5 1 5 1, suppose 4, 5 1 4 1. Hmm? No, it's not 5 1 4 1. Okay, 5 1 6 4 1. 5 1 6 4. I think that's enough. No, 5 1 6 4 2. So, what will be the total XOR of this subarray? This array. The XOR of 5 and 1 is 4. The XOR, okay, so 5 and 1 is 4. XOR of 4 and 6, 4 and 6 is 2. The XOR of 4, 4, XOR of 4 and, okay, 4 and 6 is 2. Okay, we can avoid this. And the XOR of 2 and 2 is 0. So the XOR of the total, this total subarray is 0. Now, according to our assumption, if we find a subarray such that the total XOR of this subarray is equal to 0, we will be able to split it into three. We'll be split it into three, subparts, two subparts, such that the total XOR of the first subpart will be equal to the total XOR of the second subpart. So suppose we are splitting it from here. We are splitting it here in the first case. So what is the total XOR of the first subpart? The total XOR of the first subpart will be equal to 5. Will this be equal to the total XOR of the second subpart? The total XOR of the second subpart. What is the XOR of this subpart? What is 1 XOR 6? 1 XOR 6 is 7. What is 7 XOR 2? 7 XOR 2 is 5. So it will be equal to 5. So the XOR of this part will be equal to this part. So this condition is satisfied. Now let us split the subarray here. If we split the subarray here, what will be the XOR? The total XOR of this part will be equal to 5 XOR 1 will be equal to 4. And what is 6 XOR 2? 6 XOR 2 is equal to 4. So that's also satisfied. Now let's split the subarray over here. Let's split the subarray over here. What will be the XOR of this part? The XOR of this part will be 5 XOR 1 is equal to 4. 4 XOR 6 is equal to 2. So 2 is equal to the second subpart XOR is 2. So the XOR of the first subpart is equal to the XOR of the second subpart. Okay, why is this property always satisfied? Because like the total XOR is equal to 0. So the total XOR, since the total XOR is 0, whatever first subpart we take from this the total array, it should be equal to the second subpart. Then only it will get cancelled and the total XOR will become equal to 0. So if we are able to find, if the total XOR is not 0, and if the total XOR is 0, and if we are able to find some part of this uh, array such that the some index j such that the XOR of the first part is not equal to the XOR of the second part, then that will not get cancelled, and it will be some XOR not equal to 0. So that will be contradiction to the our initial assumption. So this is what we are basically doing. So we are using two for loop. So this first for loop is used to compute the starting index. Let us say this p, this second for loop is used to compute the ending index. Now if the mm, if the starting, okay, okay, now why are we, okay, there is no need to do this. Okay, so what we are doing here is that we are taking Okay, we are taking an array from P to Q. We are taking an array from P to Q, and we are, yeah, we are taking an array from P to Q, and whether we are checking the, um, the total XOR in between P and Q. If the total XOR in between P and Q is equal to 0, we know that the total XOR between P and Q is equal to 0. We know that we can split that subarray in, we can split that subarray using some index j, and this j can vary. We can place this j anywhere inside this particular subarray. We can place this j over here, we can place this j over here, we can place this j over here, we can place this j anywhere. So how many places can we place this particular j? If the subarray is of size 4, we can place the j in 1, 2, 3. So 4 minus 1, we can place this j at 3 positions. So if this array was some size 5, okay, then we could have placed the j over here, 1, 2, 3, 4, 4 places. So as general, we can say that we can place the j in the total size of the subarray minus 1 positions. So that's what we are doing here. The total length of the subarray is q minus p, which is equal to the total length of the subarray minus 1. So these are the number of positions where we can place that particular j value. So these are the number of the triplet positions available with the starting index as p and the ending index as q. Yeah, so this is the second approach. Yeah, thank you for listening to my video. And if you understood the approach, can you please like and subscribe, and comment down below what can I improve in my explanation skills, and what can I improve in my further videos. Thank you.